Welcome to the third lecture of week 4, which is on particle dynamics, and here we will discuss some of the worked example on particle dynamics. So the topic of this lecture is particle dynamics examples. Let's consider the first example on particle dynamics. It says a spherical particle of 50 micrometer size with density 2600 kg per meter cube is falling in still water. What we have to compute is terminal settling velocity of particle. So you see, to solve this, to calculate terminal settling velocity, we should know what is the region in which particle is falling, whether it is laminar region or turbulent region. So when you see the language of this question, it will speak about the region on its own. How? Here you see the particle diameter is 50 micrometer, so that is very less. So when we consider very small particle, it is usually falling in laminar zone. If you remember the Stokes Law application, there we have discussed the small fine particle and microorganism, all these will follow the Stokes Law. It means they fall in laminar zone. So as water is still and particle diameter is very small, it will be considered in laminar region, and therefore Stokes Law will be applicable. This is the expression of Stokes Law, that is g dp square rho p minus rho f by 18 mu. This is the Stokes Law, and fluid which we have is the water. So for water density we have taken as 1000 kg per meter cube, and viscosity we have taken as 1 centipoise, which is 10 raised to the power minus 3 kg per meter second. And the parameters used for solid, density is 2600, that is given in the problem, and diameter is 50 micrometer, which is 50 into 10 to the power minus 6 meter. So all parameters are known to us, so we can calculate the terminal settling velocity directly by following the Stokes Law. So considering these value, Vt value we can obtain, which is having a value 0.00218 meter per second. So if you see this problem, how we can find the region of flow, that is purely based on particle diameter, and therefore we have used Stokes Law here. In example 2, what happens? The particle of square shape having 2.3 mm side and 1 mm thickness are falling in oil. We have to calculate the terminal settling velocity of particle. So here you see the particle is not spherical, non-spherical particle is considered over here. And the liquid is not water, but it is oil. So what is the purpose to take this example is when the particle is non-uniform, which so when particle is not non-uniform, non-spherical, how the terminal settling velocity will be computed, and this can be applicable to the real situation also, because in real situation most of the particles are non-spherical. So this example will be helpful in that condition, and the given parameters are density of the particle, that is 3500 kg per meter cube, density of oil 850 kg per meter cube, and viscosity of oil is 0.013 kg per meter second. So let us start the solution of it. Now as far as particle is concerned, that is it is having side of 2.3. So this is the square particle, 2.3 one side, another side is also 2.3. However, thickness of the particle is 1 mm. So this particle dynamics we have to calculate, we have to find the terminal settling velocity of this particle. And as far as solution is concerned, to compute the settling velocity, one should know the region where particle is falling. If you remember the last example, there we can aware about the region by considering the particle size, that was very small, but here particle size is significant. So how we can find the region in which particle is falling. Until unless I will not aware about the region in which particle is falling, I cannot calculate, I cannot know the Reynolds number, and therefore I cannot calculate Fd, and further terminal settling velocity expression cannot be used. So, to know the region we should know the Reynolds number, and for that we know the terminal settling velocity. So, you see this is all trial and error based computation, and to carry out this generalized expression of terminal settling velocity and Fd we have considered, which is shown over here. So, what happens, this is the expression of Vt as a function of Fd. Now, as particle is non-spherical, that is square in shape, so instead of dp we have to consider dv, that is the volume diameter of particle, which is defined as the sphere diameter. dv is basically the sphere diameter which is having same volume as the particle. So, to calculate dv, first of all we should know what is the volume of particle. So, if you consider this particular particle, which is the object of the present example, here we have 2.3 and this side is also 2.3. So, 2.3 into 2.3 into 1 would be the volume of particle, which comes out as 5.29 millimeter cube, or 5.29 into 10 raised to the power minus 9 meter cube. Once I am having the volume of particle, I can calculate the volumetric diameter, and that would be equal to volume of particle into 6 by pi, and the complete expression has the power 0.33. So, solving this we can calculate dV as 0.002175 meter. So, if you remember the effect of shape, particle shape on terminal settling velocity, along with dP we also know the sphericity of the particle, so that we can use the given chart of Fd and Reynolds number. So, to calculate sphericity, first of all we will define it like surface area of spherical particle having same volume as the particle to surface area of particle. So, surface area of spherical particle, we already know the volumetric diameter of particle. So, the surface area would be pi dv square. So, pi value is this, and diameter we have already calculated. So, surface area of spherical particle comes out as 1.486 into 10 power minus 5 meter square. Further, we have to calculate surface area of square particle. So, you see here how I can calculate surface area of this particle. If you see, this is one face and similar face present opposite to this, and here we have this another face which is have total 4 faces of this size. So, surface area of this face we can calculate as 2.3 into 2.3 into 2, because 2 faces are available of this size. Further, 2.3 into 1 into 4, because 4 faces are available of this size, where the area is 2.3 into 1. So, 2.3 into 2.3 into 2 plus 2.3 into 1 into 4. So, total surface area of a square particle is 1.978 into 10 raised to the power minus 5 meter square. Therefore, we can calculate sphericity as surface area of a spherical particle divided by surface area of square particle. So, it comes out as 0.75. Basically, it is coming as 0.7513, and we have approximated it to 0.75. So, now we know the volumetric diameter of particle as well as the sphericity, and this is the expression of terminal settling velocity as a function of Fd. So, further we have rearranged the expression and write the whole equation of Fd as a function of Vt. Therefore, to calculate the velocity we should calculate the Reynolds number, and as the standard graph available to us is drawn between Fd as well as Reynolds number. So, we will find the expression of Fd as a function of Reynolds number, not as a function of terminal settling velocity. So, here you see Reynolds number of particle is dV Vt rho f by mu f. So, here again we have calculated, we have considered dV, that is volumetric dia, instead of dP. And from this expression we can write the expression of Vt like Reynolds number mu f by dV into rho f. So, this Vt expression we will put over here, and final expression of Fd we can get as a function of Reynolds number. And if you see the final expression, we have Fd equal to A by Reynolds number square. Now, what is A? A is the constant where we have put all values which are constant, like particle density, fluid density, particle diameter, that is volumetric dia, and fluid viscosity. All these are constant. So, we have represented all these value as single parameter, and that is A. So, Fd equal to A by Rep square, that is the expression we have got. So, considering value of known parameters, that is rho p, rho f, mu f, g and dV as 3500 kg per meter cube, 850 kg per meter cube, 0.013 kg per meter second and 9.81 meter per second square, and 0.002175 meter as volumetric dia. So, considering all these value, we can calculate value of A, which comes out as 1794.068. So, this expression we have already known as far as its value is concerned. So, now we have expression of Fd as 1794.068 divided by Reynolds number square. If we take the log of this expression, so ln Fd, that is natural log Fd equal to ln 1794.068 minus 2 ln Reynolds number. So, if you see here, we have Fd as well as Reynolds number based on logarithmic form, and for further calculation we have taken Reynolds number as 1, because once I take the Reynolds number as 1, this complete expression would be equal to 0. So, when Reynolds number is 1, Fd value is 1794.068, and when we take Fd as 1, then this expression would be 0. Reynolds number comes out as 42.356. So, these value will be used to calculate the Reynolds number of particle. So, you see here we have the value of Reynolds number and Fd. Corresponding to Reynolds number 1 value, Fd is coming as 1794.068, and Fd equal to 1, the corresponding value of Reynolds number is 42.356. So, using these values we will calculate the Reynolds number. How we will calculate this? We have already computed what is the sphericity of the particle, and it is coming out as 0.75. Now, if you see all these plots, here we have this is 0.125, and the third plot is of 0.6 and fourth is 0.806. So, between this we can have the value of 0.75. Now, to point out that value, first of all we have to point out these points. For example, correspond to Reynolds number 1, the value of Fd is coming as 1794, which is this point, and correspond to Fd value 1, we have the Reynolds number 42.35. So, joining these 2 points, we can basically find the governing equation, governing line in which Reynolds number is falling. And if you see between 0.6 and 0.8 sphericity, we can have the value of sphericity as 0.75. So, if you see between value 0.6 and 0.8 of psi, we can have the value of psi equal to 0.75, and whatever the plot of 0.75 cross this line, that we can consider as the point of consideration. So, here you see this point we have considered as 0.75, because if we have the plot of 0.75 sphericity, it will intersect the red line at this point only. So, considering this point, we can have this drag coefficient as well as the value of Reynolds number. So, following this point, we can have Reynolds number as 11, which we can see from this graph very easily. So, once I know the Reynolds number value, we can calculate the value of terminal settling velocity, which comes out as 0.077 meter per second. So, once I do not know the region where particle is falling and when it is of non-spherical shape, by following this method we can calculate the velocity of particle. So, that is example 2. Now, we are considering example 3. In this example, we have to calculate terminal settling velocity of a steel ball having 3 mm diameter and density 7870 kg per meter cube, which is falling in oil of density 850 kg per meter cube and viscosity 0.04 kg per meter second. Now, its solution we will start. If you see this particle we are considering as steel ball, so that can be considered as spherical particle. In this problem also, region in which particle is falling is not known. However, as particle is spherical in shape, we can use direct method using Galileo number instead of using trial and error method, which we have used in example 2. So, in this problem, we have to calculate terminal settling velocity. So, as far as solution is concerned, first of all we have to find the region in which particle is falling, and if you read the problem, region is not defined over here, and we also did not know what expression we have to use. And to know the expression, first of all we should know the region, and to know the region we should know the Reynolds number. For that we need the terminal settling velocity, so that is trial and error method. But in this particular problem we are considering steel ball, and this steel ball is we can assume as spherical in nature. So, instead of using trial and error method, we can use direct method using Galileo number. Now, as far as this approach is concerned, here we have the expression rho dash by rho u naught square into Reynolds number square, which is equal to 2 by 3 Galileo number. And as far as Galileo number expression is concerned, it is like this: d cube rho s minus rho into g divided by mu square. So, that is the Galileo number expression in which all parameters are known to us. So, first of all we will calculate the Galileo number for this example. So, considering value of diameter as 0.003, density of particle 7870 and that is of oil 850, and considering viscosity of fluid 0.04, we can calculate Galileo number, which comes out as 987.9. So, once I have the Galileo number, I can find the value of this particular expression, that is equal to 2 by 3 into Galileo number. So, 2 by 3 into 987.8, it gives the value 658.53. So, this expression value we already know. So, how we will compute the terminal settling velocity? First of all, we will use the graph for computation purpose. This is the expression which has value 658.53, and this is the graph. If you see, this y axis is basically this particular parameter and x axis has the Reynolds number value. So, you see here 658.53 we have to draw, and this will fall somewhere here, and when it cut this curve and corresponding value of Reynolds number we can trace from the x axis. So, when we do this, Reynolds number, that is Re dash, comes as 25, Now for this Reynolds number, we can calculate terminal settling velocity of particle, which is coming as 0.39 meter per second. So this is one way for computing the terminal settling velocity of particle. Here we have used the graph. Further, the same computation we can done using the table, and if you remember, the table has the value in terms of log. So first of all, we will calculate log of this value, which is basically log of 658.53, and it is coming out as 2.8186. And the data is available in this table. If you see this, here we have the data of log r dash by rho u square by r e dash square, and here also we have the data in decimal form, and all these data which are shown in this table are basically the log of Reynolds number values. So here we have to find the value of Reynolds number corresponding to 2.8186. So if you see here, we have the value of 2 and 0.8 will lie over here. So we will use this parameter. Further, it is 2.8186. So again we have to find the value correspond to 2.9. So 2 is here and 9 is here. So value is 1.419. So value of Reynolds number corresponding to 2.8186 will lie between 1.346 and 1.419. And how we can find this value? By interpolation. So when we do the interpolation, then log re dash we can find as 1.36, and corresponding Reynolds number value is coming as 22.9, and therefore we can calculate velocity as 0.359. So in this way we can calculate the velocity. Once I do not know the region, we can follow this direct method, but it is specifically used for spherical particle. If we have to calculate the settling velocity of non-spherical particle without knowing the region, we can follow example 2. Now we have example 4, where a spherical particle of silica of 0.1 mm diameter falls in water filled in the glass cylinder of 40 mm internal diameter. Estimate the settling velocity of single particle of silica, and here mass ratio of water to silica is given as 5. These are the parameters. For solution, first of all we will estimate the terminal settling velocity of single particle, which is considering in part 1. For example, if I am considering laminar region where particle is falling, so Reynolds number should be less than or equal to 0.1, and this is the expression of Reynolds number which must be less than 0.1. So in this case Stokes law will be applicable. So putting the values in this expression, we can calculate terminal settling velocity, which is coming out as 0.8993 meter per second. Now once I have this value, further we will calculate the Reynolds number for verification, and if we calculate Reynolds number, it is coming out as 0.89925, which is greater than 0.1. So Stokes law is not applicable here. Let us consider second region, where FD is defined as 24 by RE plus 0.44, and this is the generalized expression for FD. So putting FD over here, we can have the expression in terms of Reynolds number. This is the final expression, and when we solve it, Reynolds number is coming out as 0.88489, which is falling between 0.2 and 500. So this region is correct, and consequently we can calculate value of velocity, that is 0.11 meter per second. In this case, as the particle is falling in a container of 40 mm diameter, we can have the wall effect also. Now wall effect, if you remember the expression of CF, it is defined for turbulent as well as laminar region, but here it is falling in transition region. So we will calculate CF using both expression, and this value we are getting for laminar flow and this is for turbulent flow. Among this we will select the larger value, which is 0.9963. Considering this factor Cf in terminal settling velocity, which we have found in last slide, we can calculate final terminal settling velocity, which is coming out as 0.1096 meter per second. So, that is the part 1 of this. Now, part 2 is here we have to consider the mass ratio of water to silica. It means here we have amount of silica available in water, and it means that there are number of silica particles, and therefore, we will follow the hindered settling velocity expression here. So, first of all we have to calculate volume fraction, that is 5 by rho f by 5 by rho f plus 1 by rho s, because 5 fraction of water and 1 fraction of silica. Considering this, we can calculate epsilon as 0.9298. Once I have epsilon, we can calculate Fs, that is settling factor, by this expression, which is coming out as 0.6443, and after computation of Fs, we can calculate hindered settling velocity, which is the terminal settling velocity into Fs. So, finally, hindered settling velocity is coming as 0.0706 meter per second. Now, here we have fifth example in which bacteria of 5 micrometer is moving in a water in 10 mm per second velocity. So, what is the drag coefficient on the bacteria, that we have to calculate. Now, to calculate drag coefficient, Reynolds number should be computed to know the region of flow. So, Reynolds number we can calculate because we know the velocity. So, it can be directly calculated, which is coming out as 0.05. So, it is less than 0.1. So, Stokes law will be applicable over here, where Fd is 24 by Re. So, Fd we can calculate, which is coming at 480. So, that is the drag coefficient value on the particle. So, that is the drag coefficient on the bacteria. And here we have another simple example. So, in this example, we have to calculate settling velocity of glass sphere having density 2467 kg per meter cube and diameter 1.5 mm, and this is falling in water. So, slurry contains 65% by weight of solid, and we have to use the Newton's law. So, region is already given to us, that it is falling in turbulent region, and we have to use the Newton's law. As 65% weight of solid is available, obviously we will calculate the hindered settling instead of terminal settling. So, first of all we should know epsilon value, that is if 65% solid is available, so 35% water will be there. So, 35 divided by rho f divided by 35 by rho f plus 65 by rho s. So, epsilon value is coming as 0.5705. Considering this, we can calculate the Fs value, which is coming at 0.0538. Once I know this, I can calculate the hindered settling velocity, but for that we should know the terminal settling velocity. As Newton's law we can apply, which has this expression. While putting all values in this, we can have terminal settling velocity as 0.2558, and when we multiply this with the Fs value, the hindered settling velocity or final velocity of the particle is coming as 0.0138 meter per second. So, here we have the summary of this lecture. In this lecture, different worked examples are considered to illustrate the computation of terminal settling velocity of particle. Spherical as well as non-spherical particles are considered in worked examples. Direct as well as trial and error method are used to compute settling velocity of particle, and these are the references. That's all for this. Thank you.